Greetings to all of my wonderful summer 307 students. It is my pleasure to welcome you to this video. So in this series of videos, I'm going to be talking about a particular inferential statistics test known as a one-way between subjects ANOVA. So whenever we conduct a one-way between subjects ANOVA, what we are endeavoring to do is we're comparing 3 or more separate groups on the same outcome variable. And we'll talk about what this means in just a second. So the inferential statistical test that most of you are probably already familiar with is the independent t-test. So the independent t-test has a lot in common with the between subjects ANOVA. So for example, we would conduct both an independent t-test or an ANOVA when we have a dependent variable that is continuous or quantitative, okay? And we would also conduct both an independent t-test and a one-way ANOVA when we have an independent variable that's categorical. Okay, so that's true of both of these types of tests. We have a continuous dependent variable and a categorical independent variable. The only difference between the independent t-test and the one-way between subjects ANOVA is that with an independent t-test, our categorical independent variable has 2 levels, whereas with the one-way between subjects ANOVA, we're trying to compare 3 or more separate groups of people on the same continuous dependent variable. Okay, so with the independent t-test, we have 2 groups of people performing a task at the same time, and we're comparing performance between those 2 groups, whereas with the one-way between subjects ANOVA, we now have 3 or more groups that are completing the same task or dependent variable. Okay, so a couple of things. Why do we call the between subjects ANOVA a one-way ANOVA? Well, that's because we are comparing all 3 groups on a single independent variable. So we have one independent variable and one dependent variable, right? But it is possible to conduct what's called a two-way ANOVA, where we actually have 2 independent variables that are both affecting the same dependent variable. Okay, so we'll talk about that next. But for now, we're going to focus on a one-way ANOVA where we have 3 or more separate groups of people, a single independent variable affecting one dependent variable. Okay, so let's look at this distinction a little bit more closely. So some of you might remember from 306 the distinction between a between subjects and within subjects design. Okay, so with a between subjects design, we have multiple groups of people completing some kind of experimental task at the same time, right? So for example, maybe we have one group of people reading a text and another group of people making, not just reading the text, but using some kind of mnemonic device, right? And we're looking at their memory for the text, right? So right there we have our categorical independent variable, which is study task. We have read only versus reading plus use of a mnemonic, okay? And then we have our dependent variable, which like I said is just memory for the text, right? So that's kind of your classic between subjects design, okay? And if you had just those 2 groups, then the statistical analysis that you would conduct is an independent t-test, right? Whereas if you had 3 or more groups, right? So let's suppose we have one group that is reading the text, one group that is testing themselves on the text, and one group that is using some kind of mnemonic device. Okay? Then we have a categorical independent variable with 3 levels, and we would do a between subjects ANOVA. Now let's look into what we call a within subjects design. Right? So with a between subjects design, you are comparing different groups of people to each other, right? Whereas a within subjects design, you're comparing the same group of people at 3 different points in time, right? So if we were to make this a within subjects design, maybe we would have people first read a passage, okay? And then after a distractor task, we give them a different passage and have them take a test on it instead of reading it, right? And then we have them read a third passage where they use some kind of mnemonic device, okay? That would be a within subjects variable because we're looking at change in the dependent variable, okay, over time in the same participants, right? So that would be a within subjects ANOVA because we have that same continuous dependent variable, but we now have 3 levels of our categorical independent variable, okay? Another sort of classic example is maybe some kind of biomedical or psychopharmacological pharmacological research, right? So maybe we are looking at the efficacy of placebo versus an antidepressant versus that antidepressant plus psychotherapy, right? So we have participants come into our laboratory. We give them a baseline depression questionnaire. And then for 6 weeks, they take a placebo, and we again look at their levels of depression. Then for another 6 weeks, they take the depression medication, and we again look at their depression. And then for 6 weeks, they have the antidepressant plus weekly therapy with a psychologist, right? And then we look at their depression scores again, right? So what we are looking for then is the change in depression score over time as a function of the type of intervention, okay? So that would be a within subjects ANOVA. Okay, so just to summarize, when do we use a between subjects ANOVA? Okay, whenever we are comparing 3 or more groups of people in an attempt to find some kind of difference in our dependent variable, right? So for example, we might ask, does income differ between the 5 boroughs of New York City, right? So we would have 5 different neighborhoods. We would sample people from those neighborhoods, ask them for their income, and see if they differ as a function of where people live, right? Another example is if we're looking to see if there's a relationship between class year and hours of studying, right? So maybe one hypothesis would be that upper class students, juniors and seniors, have the benefit of prior experience, right? And know that the more they study, the more successful they'll be in their classes. So maybe we would expect hours of studying to increase linearly as people advance in college, right? So we would collect a sample of individuals who are freshman, sophomore, senior, and junior, okay, and look at whether there is a difference between those groups in terms of hours of studying, okay? All right, so hopefully that makes sense. Another thing to emphasize is that whenever we are to conduct a between subjects ANOVA, there's 2 steps in the process, okay? So the first is to figure out if there are any differences between our groups, okay? So the first thing we learn when we calculate our statistics is, yes, there's a difference, or no, our groups are not equal to each other, okay? and that's the first part. And the first part we will do by hand. So you'll actually use like a critical value table and do a process that's very, very similar in some ways to the independent t-test. Okay? And then we're going to use SPSS to figure out where the differences are. Okay? So the first thing we learn is simply, yes, there is a difference in hours studied across freshmen, sophomores, juniors, and seniors. Okay? And then we have to use SPSS to find out which groups differ from each other. Okay? So one question you might have is, why do we have to do a separate type of statistical test? Why do we have to use this ANOVA? Why can't we just run 3 different independent t-tests, right? That would certainly be simpler, right? But there's a caveat whenever we conduct any kind of statistical test, and that's what's known as a type 1 error. So anytime we conduct a t-test or any other inferential statistics test, there is a 5% chance of us incorrectly rejecting the null hypothesis when the null hypothesis is actually true, right? So that's not a very big chance, right? There's a 95% chance that if we were to reject the null hypothesis, we would be correct in that, right? But there's a 5% chance of committing a false positive, right? Of saying that that we can reject the null hypothesis when in actuality the null hypothesis is true, right? But if we were to conduct 3 separate independent samples t-tests, that would mean that we keep accruing that 5%. Right? So instead of a 5% chance of rejecting the null hypothesis when the null hypothesis is true, we now have a 15% chance, which is much, much, much higher, right? So instead we do an ANOVA. And what the ANOVA allows us to do as an omnibus test, which is called an omnibus test, is it allows us to compare several different levels of the independent variable at the same time, okay, without accruing that additional risk of making a type 1 error. Okay? Okay, so like I said, the inferential statistics test most of you are probably familiar with is either an independent samples t-test, a dependent samples t-test, or even the one sample t-test, if you remember that, right? And in that case, our statistic that we were calculating was t, right? Now that we're talking about ANOVAs, though, we have a new test statistic known as F. And the formula for F is actually quite simple, okay? The formula for F is a fraction, a simple fraction, and it is our variance between groups over the variance within groups, okay? So we're essentially looking at the dispersion of scores about the mean, okay, between groups of people and also within the same groups of people, okay? And we find that our F value gets larger, okay, because of this formula, right? Our F value gets larger, obviously, when the differences between groups get larger, okay? But also when the differences within groups get smaller, okay? And that's part of the reason why, that's the main reason why ANOVA stands for analysis of variance, because we're comparing two different measures of variance. The variance between different groups of people and the variance within the same group of people. Okay? And we use the same process, guys. So you remember when we talked about t-test, we talked about the critical value and how we compared our obtained statistic to a critical value to determine if our alpha level was greater than or less than 0.05, or if it falls within the rejection region. Right? So we're going to do the exact same thing. We have a table of critical values, and we're going to compare the F statistic that we calculate to a critical value in the table, okay? And we're going to do it the same way. We're going to choose our alpha level of 0.05, and we're going to use degrees of freedom, okay, to find that value, and that's going to tell us whether our difference is significant or not. Okay, so this is the point, I should warn you, where students start to get a little bit intimidated because there are several components of the formula to calculate F in the between subjects ANOVA. But the calculations in and of themselves are actually quite simple, okay? So just hang in with me a little bit and try to memorize, if you can, each of these notations, right? Because they're actually very simple. It just looks a little bit intimidating when we see them all together. But just hang with me for a little bit, and I promise we'll go through it step by step. Okay? So we'll start with the green notations here, right? So first we have a capital N, right? And I'm sure all of you will remember from 306 and other stats classes you may have had that N simply refers to sample size, or how many people are in a particular group, right? So a capital N is capitalized to denote total, okay? So it's basically just notating how many people total do you have in all of your groups, right? Because remember, with the between subjects ANOVA, we're comparing different groups of people. So how many people total do you have in all of your groups, right? And then we have in sub 1, in sub 2, and in sub 3, okay? And all that means is how many people are in group 1, how many people are in group 2, and how many people are in group 3, okay? And you can designate whatever level or group you want to stand in for 1, 2, or 3. It doesn't matter, okay? And then we have K, and that is the total number of groups, or alternatively, the total number of levels of your categorical independent variable, right? So when I first proposed that study where we're looking at people's memory, right? We have one group that reads, one group that tests themselves, and one group that uses a mnemonic, right? So we have one categorical variable, type of task, right? And it has 3 levels or 3 groups of people, right? So K is equal to 3. Okay. All right, so hopefully that was fairly simple. Now let's move on to the notations in blue. Okay? All right. So we have capital G, and again, when you see a capital letter, you should think total, right? So grand total, okay, or the sum of the scores from all of the groups, okay? So this time we're not looking at how many people are in the study, okay? We are looking at the total or sum of all the scores, okay? So in the study I was just talking about, right? I would have a column that notes memory score, and maybe it's memory score out of 30. So I break down the passage that people read or tested or used a mnemonic device for, right? So for each person in the experiment, I have some number out of 30. So to calculate G, I would just add up all of those scores and I would probably get a fairly large number. Okay, that's G. Now we have T sub 1, T sub 2, and T sub 3. Okay, and what these are is they're similar to G, but instead of adding up all the groups, you're just adding up the sum of all the scores in group 1, all the scores in group 2, and all the scores in group 3. Okay? And then you're going to calculate something that should be familiar to you, which is the sum of squares. Okay? And to do this, you're going to square each person's score and then add them all up. Okay? And this is all of the information that you need to start calculating the one-way ANOVA. Okay? So take a deep breath, think happy thoughts, and we're going to go to our F table to start using our formulas. Okay? Okay, so here is our formula table, okay? And again, I'm going to show you guys an example in the next few slides, and we're going to take this one step at a time, okay? So don't worry, just stay calm, stay with me, okay? But I want you to notice that all of the notations in the table we've already defined, right? So we have the sum of squares, for example, minus the grand total squared over capital N, okay? And we know what K is, we know what capital N is, okay? And SS just means sum of squares, okay? So we know what all these numbers are. DF means degrees of freedom, which you guys are used to calculating for the t-test, okay? So all of these concepts are very familiar to you, okay? They're things that you've seen before, okay? But I'm going to show you guys an example starting in the next slide, and we'll take it just nice and slow, step by step. Okay, so here is our example problem. All right, so our research question is, do high school students, undergraduate students, and graduate students differ in terms of how many cups of coffee they drink per week? Okay, so that's our research question, and here is our data, right? So we have 3 different groups of people, high schoolers, undergrads, and grad students, okay? Our sample, our total sample, is comprised of 15 students, okay? Our independent variable is education level, and we have 3 different levels, which are categorical, right? High school, undergrad, grad school. And then we have number of cups of coffee per week, which is quantitative or continuous, right? Okay? And the first thing we always do whenever we conduct an inferential statistics test is we state the null hypothesis, abbreviated H sub O, and we state the alternative hypothesis or the researcher's hypothesis, abbreviated H sub A. Okay? So the null hypothesis is always essentially that the groups do not differ, or there is not a significant difference between the levels of the independent variable on our dependent variable. Okay? So stated very simply in words, the null hypothesis says all 3 groups of students drink the same amount of coffee, or the groups don't differ in terms of coffee consumption. Whereas the alternative hypothesis does hypothesize that there is a difference. Okay, so there's at least one of these groups is different from at least one of the others. Okay, Or another way of saying that is that there is some relationship between education level and coffee drinking. Okay? So again, the first step in the process when we calculate our F statistic is simply going to tell us there is a relationship or there is a difference. Okay? At least one of the groups or at least one of the levels differ significantly from another one of the groups or another one of the levels. If we want to find out which groups differ, okay, we have to use SPSS to conduct what are known as post hoc tests. Okay, but we'll do that in just a little bit. For now, we're going to focus on calculating our F statistic. Okay, so again, this is our sample. Okay, so in the next slide, I'm going to show you how to make a really handy dandy table that will make it easy for you to calculate all of the information that you'll need when you get to your F table. Okay? Okay, guys, so this is our table that we're going to use to organize all of our data and calculate all of the components that we need. So, in fact, I would recommend when you do the practice problem, okay, which I'm also going to go through, there's going to be a video with the practice problem, that you copy and paste this table and just change, obviously, the scores in it and use it to calculate your F value as well, okay? But here, so here are the components. The blue and the pink and the green are denoting each of our levels of our independent variables. So we have the data for high schoolers, the data for undergrads, and the data for grad students, okay? And we have 3 columns here, okay? So X is just the number of cups of coffee, right, from our data set directly, okay? X squared is obviously the score squared, okay? And then what is T? T is the sum of the scores in each group, okay? So again, for high school, we have X is 2, we square that and get 4. X is 3, we square that and get 9. 0 is 0, 1 is 1, and 4 is 16, okay? And then to calculate T, we just add up all those values of X. We have 2 plus 3 is 5, plus 0 is 5, plus 1 is 6, plus 4 is 10, okay? So we do the same thing. We input the scores directly from our data set. We square those scores, and then we add up all the values of X, and that's how we get 14, okay? And we do that again for grad students. So we input our scores directly from the data set here. We square each of those values of X, and then we add up this column, and that gives us 26. Okay, so right there we've got X squared, and we've got T. Okay, so let's start with the easiest calculation, right? So we know that our total in, or the total number of people in our study is 15. Okay, so now we need to calculate the number of people in each of our groups, right? And if we were to count the values of X, we would see 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, right? So we know there are 5 people in each of our groups, our 3 groups, for a total of 15, okay? And then we would input our T for each of our groups as well, right? So again, our T is the total value of X in each group. So we have our T is 10 in blue here. Our T is 14. So our T is 10 for high schoolers, 14 for undergrads, and 26 for grad students. Okay, so right away we're kind of seeing evidence in support of our hypothesis, right? So grad students are drinking over twice as many cups of coffee compared to undergrads, right? All right, and then we have G, and G is simply the sum of the scores from all groups. Okay, so if we add up each of those T values here, we'd have 10 plus 14 is 24, plus 26 is 50. Okay, all right, so hopefully this is pretty simple so far. But certainly if you have any questions, don't hesitate to text me or email me as far as where I'm getting these numbers from. And then the very last thing we need to do is we need to sum up this column, right? So we just take the sum of the x squared column, okay? So if we were to add up all of these values, we would get 228, right? So G is the sum of all of the values of x, okay? Whereas the sum of squares is going to be the sum of all of the values in the x squared column, okay? So that's where we have our 228, okay? So just again to summarize, we have a total of 15 participants. We have 5 participants in each group. We have a total score for high schoolers of 10, a total score of 14 for undergrads, a total score of 26 for grad students. Our G, or sum of all the scores from the groups, okay, is right here, and it's 50, okay? And then our total sum of squares is 228. Okay, so the total in the x squared column is 228. Okay, and that's all we need, guys, to start filling out our F table to calculate our statistic, our F statistic. All right, so now we are going to use all of those simple calculations we just made to fill in our F table. Okay, so basically we are going to make 3 calculations, okay, and these all relate to variance, by the way. So these calculations are going to tell us what our variance is between groups as well as within groups, and also the total amount of variance there is, okay? So to calculate the total sum of squares, okay, we're going to take our sum of squares minus g squared over n, okay? And again, don't get intimidated, right? Because we know what all those values are. So all you have to do is flip back to the previous slide to plug in those values, right? So our total sum of squares that we calculated, that whole column, right, of x squared, was 228, and then we subtract g squared over n, right? So we know that g is just the total of all of the scores, the total of that x column across the 3 groups, right? And that's 50. So we have 228 minus 50 squared over the total sample size, which we know is 15, right? So if we plug in all of those values, we get 61.33. Okay, so that tells us our total sum of squares. Okay, and now we're going to calculate our between groups sum of squares. Okay, so the formula is the sum of t squared over n minus g squared over n. Right? Well, we know that g squared over n is 50 squared minus 15. Okay, so we have that already from our previous formula. And again, what we are doing in the first part of the formula is we are summing up t over n. Okay, and we're squaring the t. Okay, so all we need to do is to get t1, t2, and t3, okay, and square those values and divide them each by the n of each selected group. Okay, so we have, again in our table, we have group 1 was 10. That was their total number of scores, right? Group 2 was 14. That was their total number of scores. And group 3 was 26. Okay, so we square all of those numbers at the top of our fraction, and then beneath we put the respective sample sizes, which are each 5. Okay, so we sum up all of those things, and then we subtract 50 squared divided by 15. Okay, and if we do that, we get 27.73. Okay, and then we get to our easiest calculation. So when we're ready to compute our within groups sum of squares, okay, we simply take the total and subtract the between. Okay, so 61.33 minus 27.73 is 33.6. Okay, so now our next step is going to input each of these three values into our table. Okay, so the first column, like I said, is that sum of squares column, right? So we have between subjects, sum of squares we calculated was 27.33. The within subject sum of squares was 33.60. And the total sum of squares was 61.33. Okay? And what's nice about this is we actually have an opportunity to check our math, right? So obviously, right, we have a total. Our total is 61.33. So that means that 33.60 and 27.73 would have to add up to 61.33, and it does. Okay? So if you ever have a situation where your sum of squares within plus your sum of squares between doesn't add up to your total value, then you know you should probably check your math, right? Okay, so now we have our sum of squares column complete, and now we need to calculate our degrees of freedom. Okay, so you might remember from when we covered t-tests, right, in 306, that degrees of freedom is essentially the number of values that are free to vary. Okay, and this number is going to be really important when we report our F statistic, and also when we look for our critical value in the F table. Okay, but fortunately, they're a pretty easy calculation. So for between groups, we're going to take our number of levels, or K, minus 1, okay? And we have 3 levels, so 3 minus 1 is 2, okay? Our within groups is going to be our total N minus K, so we know that K is 3, we have 3 levels, and our total N is 15. Okay, so 15 minus 3 is 12. And then our sum of squares total degrees of freedom is probably the easiest to calculate. It's the same as for independent or for t-tests, and it's simply n minus 1. So 15 minus 1 is 14. Okay, so we have 2, 12, and 14. I'm sorry, I misspoke. So 15 minus 1 is 14, right? Okay, so now we are almost done with our table. We just need to calculate our mean squares values. But again, at this point, we're just inputting numbers, right? So our formula for the mean squared values is simply the sum of squares between over the degrees of freedom for between. Okay, so it's 27.73 divided by 2. Okay? And again, for the within groups, we have the sum of squares within over the degrees of freedom within. Okay? And so that's 33.60 divided by 12. Okay? And once we do those calculations, we have 13.87 and 2.80. Okay? And if we divide those, we get 4.95, which is our F value. Okay, so after all that, we finally have our F statistic. Our F statistic is 4.95. And just like we did for all of our other inferential statistics tests, right, for the T's, we're going to use a table to find our critical F value. And that's the value that we're going to compare our obtained statistic of 4.95 to see if our value falls within the rejection region and we can reject the null hypothesis. Okay? But this time we're going to use 2 different degrees of freedom, because remember, we're looking at the variance between groups as well as the variance within groups. Okay, so the degrees of freedom between groups is 2, and the degrees of freedom within groups is 12. Okay, so those are our 2 values. Okay, so the degrees of freedom in the numerator is our between subjects value, so that's 2. And then we have our denominator value, which is 12, the within groups degrees of freedom. Okay, and our alpha value is going to be set to, or our type 1 error rate is going to be set to 0.05. Okay, so when we look in the 2 column and the 12 row, we get a critical value of 3.89. Okay, and just like with the t-tests, our rule is that if our obtained statistic of 4.95 is greater than our critical value statistic of 3.89, then we can reject the null hypothesis. Okay, so it falls within the rejection region, which means P is less than 0.05, and we can reject the null hypothesis, right? So what does that tell us? It tells us there is a significant relationship between education level and how much coffee students drink per week. Okay, so we know there is some difference between one level of the independent variable and another level of the independent variable. But to find out where the specific difference is, we need SPSS, okay, to help us do what are known as post hoc tests. Okay, so post hoc tests, what are they, right? So like I said, we know that our F value, our calculated statistic, is significant, okay? But all that tells us is that some of these groups are different from each other, but it does not tell us where that difference lies. Okay, so for example, with a hypothetical study that has the levels of A, B, and C, right? It's possible that A and B are equal to each other. There's no difference between A and B. But A and C are different from each other, and B and C are different from each other, or not equal. Okay, it's also possible that A and B are different from each other, but A and C and B and C are not. Okay, or it's possible that A is different from B is different than C, and A is different than C, right? But in order to find that out, we need to utilize our SPSS program, okay? And there are a lot of different tests to choose from. If you were to open up this window in SPSS, you would have multiple options. The one that is best is what's known as the Tukey test. Okay? And I won't really get into the reasons why, but basically it is not too powerful. Okay? So it won't detect a difference when there is not necessarily a meaningful difference. Okay? So, for example, the Fisher's LSD test doesn't reduce our type 1 error, which is the whole point of doing an ANOVA. So, we don't want to choose that one. Okay? Whereas the Bonferroni correction is going to make sure that we don't have that elevated risk of getting a type 1 error, but sometimes it can be a little bit too conservative. So it has kind of the opposite effect of the LSD test, right? In that it might not detect a difference when there's an actual difference there. Okay? So the Tukey test is kind of the Goldilocks principle. It's the best choice. It's not too powerful, but it's not too conservative either. So that's kind of the gold standard for this type of statistic. Okay? So don't do LSD, choose the Tukey test. Okay? Okay, so I am going to upload a separate video where I take you guys through how to use SPSS to do your post hoc analysis, okay? But for now, I'm just going to show you the output, okay? So these are the tables that SPSS is going to generate for you that's going to help you answer these questions, okay? So the first output I have for you is descriptives output. Okay, so these are going to give you your sample size for each of the three groups, your mean for each of the three groups, and your standard deviation for each of the three levels of our independent variable. And you're going to need the n and the mean and the standard deviation when you're writing up your results in APA style, okay, which is why you'll want to have this output. Okay. Next, we have our ANOVA table. So this is the exact table that we just went through by hand. Okay. So it's always a great idea to put your data set in SPSS, not just so you can get your post hoc test and your descriptives, but also so that you can check your work and make sure that your F value is correct, right? So we see that our sum of squares is all correct. These are the values that we got, the 27.73 for between group variance, the within group variance of 33.60, and the total variance of 61.33. We also got our degrees of freedom calculation correct. Okay? And lastly, we have our F value of 4.95. And just like we found out with the F critical value, comparing the F critical value to our obtained statistic, the P value, which is indicated in the significance column, is 0.027, which means it is less than 0.05, and we can reject the null hypothesis. Okay? So lastly, we have our post hoc tests, right? So this table is a little bit tricky to read, but I'm going to walk you through it. Okay? So, basically, we have two columns. Okay? So that first column, we have high school students. Okay? And we are comparing high school students to undergrads, and then beneath that, we're comparing high school students to grad school students. So if we look over to the significance value, right, that's our P value. So we see that if we were to compare high school students to undergrad students, that significance value is 0.736, which is a lot bigger than 0.05. Okay, so in that case, we would conclude that there is no significant difference in cups of coffee consumed between high school students and undergrad students. Okay, but if we were to look in the next column, comparing high school students to graduate school students, our significance value is 0.027. Okay, so what that means is that that's less than 0.05. So there is a significant difference between high school students and graduate school students. Okay? Okay, and if we go down the table, right, where we see kind of the same thing. So up here we compared high school to undergrad, and here we're comparing undergrad to high school. And again, we see the 0.736. That tells us that's not significant. And we compare undergrad to grad school, and we see that that difference is not significant. Okay, so the only significant difference here is between grad school students and high school students, and that's 0.027. Okay? All right, so now we have all of our information and we're ready to write up our results. Okay, so each time you guys have a homework assignment or lab assignment this semester where I ask you to complete either a math problem or an SPSS problem, this is the format I want your answers in. Okay, so for all of your homework and lab problems and your exam, you're going to want to follow this format. Okay, so the first thing we're going to do is state our hypothesis, right? The researcher or alternative hypothesis, right? So we hypothesized that year in school would result in different rates of coffee consumption, right? And in parentheses there, we're going to name our levels, right? So we have high school, undergrad, and grad school, okay? So we hypothesized that year in school would result in different rates of coffee consumption, okay? Next, after stating our hypotheses in each level of our independent variable, then we're going to indicate what type of statistical tests we conducted, okay, and what we found. So a one-way ANOVA found an overall relationship between level of education and cups of coffee consumed, okay? So then we're going to report our F value, okay? And this is very similar to how it's structured with the dependent T. So we have F in statistics, parentheses, and we have our between group degrees of freedom, a comma, and then our within group degrees of freedom, okay? And then we report our calculated or obtained F value to 2 decimal places, so 4.95, and then we separate that with a comma, and then we indicate whether P is less than or greater than our alpha level, which is 0.05. Okay? Notice again, both the F and the P are in italics. Okay? And then we're ready to discuss our post hoc analyses. So post hoc Tukey analysis indicated that grad students, okay, and then we're going to include our sample size. Again, that N is italicized, and the equal sign is separated by 2 spaces, one before and one after. Okay, so when our sample size was of 5 people, grad students drank significantly more cups of coffee than high schoolers. Okay, and we report the mean and standard deviation for both high schoolers and graduate students. And again, notice we're italicizing mean and standard deviation as well as the F and P value. Okay, and we're reporting our mean and our standard deviation to 2 decimal places. Okay. Okay. and no other differences, no other group differences were significant. Okay? All right, so a few things to notice about this APA style write-up, right, is we always begin by explicitly stating our hypothesis. Then we talk about this particular statistical test we did and explain what it shows. Okay, so we provide our test statistic or F value, our degrees of freedom, which includes 2 values within and between, as well as our P value. Okay, and then we talk about our post hoc tests, indicate what kind of post hoc tests we used, and then we describe how each of the groups compare to each other. Okay, and when we do that, we report the sample size, the mean, and the standard deviation. Okay, and notice that all of the non-Greek letters are italicized. So mean, standard deviation, and our p-values are all italicized. Okay, and like I said, an equal sign has a space before and after it, and every number is rounded to 2 decimal places. You can round p-values to 3 decimal places if appropriate, but typically you're not going to report the actual p-value. You're just going to indicate whether it's less than or greater than 0.05, okay, which is 2 decimal places. Okay? All right, so the last slide I have for you guys is your practice problem. Okay? So this problem you're going to do on your own, and it's asking whether how you dress affects your behavior or performance. So in one study, participants either wore a doctor's coat, a painter's coat, or saw a doctor's coat but didn't wear it. Okay? And then they completed a visual search test, and these were their scores, right? So again, we have a categorical independent variable of dress. We have 3 different levels of our categorical independent variable: those who wore a doctor's coat, those who wore a painter's coat, and those who simply saw a doctor's coat, right? And then our dependent variable is continuous, and it's score on visual search test. Okay, so go ahead and calculate this, your F value on your own, and the next video you see will be my explanation of the practice problem. All right, so I hope you guys have a great day, and I will see you in my next video.